So we've got this differential equation here. We've got the second derivative of y minus 3 times the derivative of y plus 2 times y equals 0. And we've got these boundaries here which look quite interesting. We've got y of log of 2 is 2 and y of log of 7 equals 7. So something quite interesting going on there. Log of 2 we know is approximately 0.69. That's a really famous transcendental number. And log of 7 is also a transcendental number, and that's approximately 1.95. So you could be looking at 0.69 approximately is 2, 1.95 approximately equals 7. But these are going to be exact values. Okay, so how are we going to solve for this? Well, we're looking for a solution for y of x. That's what our goal is for this whole question. And y of x is going to be in the form of something like a times e to the power of something multiplied by x. We don't know what these constants are, but a and lambda are what we need to find out. And there may be more than one term, so it could be a b plus e and lambda 2x as well. So we're going to have to look into that. So we're going to have to make our rules here where a and our lambda are in the integers. Okay. So, as we know, our solution is going to be in this kind of format. Why don't we find our second derivative of e to the lambda x and our first derivative of e to the lambda x, and then maybe we can work out some constants from that using our boundary conditions. So, let's first of all find the derivative of e to the lambda x. So, the derivative with respect to x of e to the lambda x, that equals lambda comes to the front because that's the constant multiplied by x, and the input for the exponential stays, so that just becomes lambda e to lambda x. And then here we've got the second derivative, so our second derivative of e to the lambda x, that's just the derivative of this. So here we've got e to the lambda x. We multiply both by lambda, so lambda squared e to the lambda x. So lambda squared e to the lambda x. Okay, so now I've got my format for my first and second derivative, and I've got my y here, which is going to take this format. I can now set them equal to 0. So d squared y dx squared, that gives me lambda squared e to the lambda x minus 3 times my first derivative, which is lambda e to the lambda x, plus 2y, and we don't know this constant yet, so I'm going to leave that out, but e to the lambda x. So our goal is to find this constant. There may be more than one, but we're going to find out as we get through it. Now, how can we solve that? That looks like quite an intimidating looking equation. Well, I've got e to the lambda x in all of these terms, so let's factor that out. E to the lambda x, so now I'm going to be left with the lambda squared minus 3 lambda plus 2, and I can set that now to 0. Okay, well, how can I solve this? Well, if I could set that to 0, I could solve it. That would even factor. But e to the lambda x is just giving me a bit of a problem here, so let's just have a quick look at that. Well, the exponential function here, we know that that will never equal 0. So if that never equals 0, for this thing to equal 0, we must have this bit here must equal 0. So therefore, what we're trying to solve here now is this equation here. So divide both sides by e to the lambda x. So divide this side and this side. This will stay as 0. This will just turn into a number 1. So now we've got lambda squared minus 3 lambda plus 2 equals 0, which you can quite easily factor out. I've got lambda minus 2, lambda minus 1 equals 0. So my values of lambda, I've got two choices here. I've got lambda 1 equals 2, and I've got lambda 2. Okay, so now I can plug these two lambda solutions into my function here for my y of x. So now as I've got two solutions for lambda, I'm now going to have two terms. So my y of x is going to be equal to AE. Now I've got lambda 1, so I've got e to the 2x. And then I'm going to have to add on my other one, which I'm now going to call my constant b, and that'll be e to the 1x, which is just e to the x. So that's going to be the form of my solution. So I'm going to take this here, this form of solution, and what I'm going to do is I'm going to plug in my boundary values, then hopefully I can solve for my a and my b. So let's clear off the board and let's go into that setup. Okay, now let's plug in some boundary values and see where that gets us. So I've got y of log of 2 equals 2. So using that one first, my x input is going to be log of 2, which gives me a value of 2. So this is going to equal 2 at x equals log of 2. So let's just put a note here, x equals ln 2. And then we know that equals 2. So let's plug that in. So y of ln 2 equals 2. So I've got a e to the 2x. So a e and then 2x, I've got 2 ln 2. Okay, so now b e to the x. So now I've got b times e to the ln 2. Okay, now using my product of my logs here, 2 ln 2 is just the same as the log of 2 squared. So let's bring this down with that written in there. E to the 2 will come up to the top there. So I've got e to the ln of 2 squared plus b e to the ln of 2. Now, exponential and log are inverse functions, so these are going to cancel out. So that's quite nice when that happens. And now it's going to be leaving me with 2 equals, well, 2 squared, so that's going to give me 4a, plus b times 2, so that's plus 2b. So that's the first part of my building blocks for my answer. So I'm going to have to bear that in mind. So it looks like we're heading to a simultaneous equation territory. Let's try for the other boundary condition. Y of ln 7 equals 7. So here I've got x equals log of 7. So I'm going to have a similar kind of thing going on here with these equations. So now I've got y of log of 7 equals 7. So that equals a times e to the 2 times ln 7, using this function here and copying the way that this one's been done. So 2 times our x, which is log of 7. 2 times log of 7. And then my next one is b times e to my x, which is log of 7. Okay, so using that same law here with the multiple of logarithms, we just need to square this 7. So let's put that in. So now I've got a e to the ln of 7 squared plus, let's bring that down here, plus b e to the ln 7. So nothing's going to change with that one. Okay, so now exponential and logarithm cancel each other out because they're inverse functions. So now I've got 7 equals 7 squared times a, it's going to give me 49a, plus b times 7, that's plus 7b. Okay, so there's another building block for my final answer. So now let's take this off the board and let's do some simultaneous equations, and hopefully we can find our final solution for this question here. Okay, so now I've got my setup to hopefully try and solve for my constants a and my b. That's my goal now, and then I've got my final answer. So 2 equals 4a plus 2b, and 7 equals 49a plus 7b. Now let's get these b's equal and then let's subtract it. So if I multiply this one by 7, multiply this one by 2, and then we'll get somewhere. So now we've got 14 equals 28a plus 14b. That looks right. And then multiply all of these terms by 2. So now I'm going to get 14 equals 98a plus 14b. Okay, great stuff. Now I can subtract. So now if I subtract these terms, I'll have a 0. 28a minus 98a is going to give me minus 70a. And then these are going to disappear. Okay, so now I've got minus 70a equals 0. So therefore my a equals 0. We can definitely conclude that from that part of our equation. Okay, so now with my a equals 0, let's plug that into this part. So now I've got 2 equals 4 times 0, because my a I've set to 0, and then 2b. So therefore 2 equals 0 plus 2b, therefore b equals 1. Okay, so that's my constants found out for my solution here. So therefore y of x equals a times e to the 2x plus b e to the x. Well, a is 0, so this term is now going to disappear, and I'm going to be left with b e to the x. Well, b is just 1. So therefore my final answer is y of x equals e to the x. And that's a very interesting solution to a complicated looking differential equation. Okay.